Hey everybody, how we doing? I miss you all. Here comes your chapter 10 review. Confidence interval hypothesis test for one sample means. Just to let you know that I know you saw some language in AP Classroom, matched pairs, and 2 sample will be coming in chapter 11. Okay, so the first thing I want to do is talk about some old stuff a little bit. That you may have forgotten. First is p-value interpretation, and we had a p-value interpretation on our team test, which I believe I screwed up the context for, but anyway, p-value interpretation is assuming the null hypothesis is true. You want to put the context there of the null hypothesis. So I'm just going to underline that. Assuming the null hypothesis is true, there is a blank % chance. Okay, and this is your p-value % chance of getting a sample. This or more extreme or unusual. Assuming the null hypothesis is true, there is a p% chance of getting a sample this or more extreme. I don't know if that comma should be there. It's fine. Okay, anyway, so that's kind of old. Another old thing I want to touch on is type 1 error. The sample taken leads us to believe we should reject the null hypothesis of whatever when we should have failed to reject. The sample taken leads us to believe we should reject the null hypothesis, so we just got a really weird, unusual sample, made it look like the whole population was weird and unusual, but it wasn't, so we should have failed to reject. Type 2, the sample taken leads us to believe we should fail to reject the null hypothesis of blank when we should have rejected sample taken leads us to believe we should have failed to reject the null when we should have rejected. So the whole population is really weird and unusual, but we got a very common looking sample. Okay, and the next thing is our little diagram for power. I'm going to try to find it. Back up a bit. Okay, let's get this note. Okay, so just a quick review of power. This is in the chapter 8 review, by the way, if you want to take a look at that to follow along. The probability that the null hypothesis will be correctly rejected is the power. The power is on the left side of the curve, and the probability of the type 2 error beta is on the other side. These are complements of each other, which means that they add to 1. You can increase power by increasing the alpha, which is the significance level, or you can increase the sample size. That, I believe that was also on the team test. Determine increase alpha, increase sample size. So if you were looking for any of this for your team test, that's where it was located. Next thing I want to talk about is the central limit theorem. Okay, so now we're finally to chapter 10. Okay, and the central limit theorem was the day that we were filling out the little chart with the green, red, and yellow dots and deciding if something was normal enough to use a normal approximation. So the central limit theorem, I'm going to draw a picture to kind of describe it. I want you to think of this as a population. I'm going to make it super skewed here. So I have a skewed population. Okay, out of this skewed population, we're taking a sample. So we're going to take maybe 2 here, here, here. Let's just say this is our sample. From this population, so I'm hoping you guys can see I grabbed a couple of these. This is random sample, this one and this one, and then what I did was I calculated the mean of that sample. So I took whatever this is, this plus this plus this plus this divided by 4, and calculated the mean, and I kept doing that repeatedly until I got a graph that looks like this. Because you're dropping means in, the means are all going to be more toward the middle, and these are the sample means, all dropped in here. So this is happening repeatedly, taking a different sample, dropping in the average, taking a different sample, dropping in the average, and this is our approximate sampling distribution. Okay, the cool thing about this, oh, you can't see him. That's gonna be fun for me. Okay, so the cool thing about this is you've got this like crazy skewed population, but because you're working with averages, your sampling distribution is gonna come out pretty nice, bell-shaped. So we learned 2 things from the central limit theorem previously. First, if your population is uniform or normal, then your sampling distribution is normal enough for any sample size. Okay, so that's the first thing. Remember, in this case, I want you guys to think about that one problem we did, which was number 59. Right at 10-59. I can flip back to it real quick. And right here, we had 18, I believe, as our sample size. But they gave us a little dot plot that showed no extreme skew or outliers. So we were able to satisfy the CLT by looking at the little graph that they gave us. Okay. Okay. If your population is not uniform or normal, so like this guy here, then your sampling distribution is normal enough for sample sizes greater than or equal to 30. So what do we use this for? We use this for satisfying the large counts condition. Okay, that looks pretty. Okay, now next topic is t-distribution. Okay, so flipping this over. Okay, so the t-distribution, it has more area in the tails, and there are different t-distributions for each degrees of freedom, if you remember. I like to create my t-distribution so that it doesn't really touch the x-axis, so that you can see the heavier area in the tails. If it was a normal curve, this would have come down and sort of touched right here. But this is my t-distribution graph, and when you guys make a t-distribution graph, you need to make sure to label the degrees of freedom on it, because that is the only thing that that identifies which t-distribution it is. Remember, there are infinite t-distribution graphs for each degrees of freedom. Let me show you the beautiful picture we made. 10-41. If you want to look at 10-41 at all, right here, it's so beautiful. Standard normal distribution is on the top. Notice it comes down, it's higher, it comes down, touches here, and then t-distribution of degrees of freedom 2 is somewhere in the middle, degrees of freedom 1. Okay. As degrees of freedom increase, the curve approaches the standard normal distribution. All right. Okay, so a couple of things. There is TCDF, which is low, high degrees of freedom. TCDF is used when you have a t-value and you want to find the area. So this gives you area. And then you have inverse t, which requires an area to the left and degrees of freedom, which will give you a location on the x-axis. All right. Confidence interval. For a one sample mean mu. Okay, identify. We wish to estimate mu equals, okay, and then you've got some kind of context here at some kind of confidence level. We wish to estimate mu equals the mean minutes of Miss Side's videos at blank % confidence. Ha. Okay, hold on. Conditions. I saved that. Did you see how I saved that? Okay. Random, independent, large counts. Okay, so random, context of the problem. Don't write the word context, please. Context of the problem or assumption. Independence is n times 10 is less than or equal to the population, or some kind of assumption. In the large counts condition for these, we want to use the central limit theorem. So n is greater than or equal to 30, so CLT applies, or check a graph, or assume. Okay, calculate. Okay, so here's where you guys might have gotten a little stuck before on whether to use T or Z, and the calculate will tell you. So if sigma is known, which is the population standard deviation, and this is very rare, your confidence interval will be the sample mean plus or minus z star times sigma over the square root of n. Okay. If you only have the sample standard deviation, which is going to happen most of the time for these problems, then your confidence interval will be x bar plus or minus t star Okay, now just a reminder, t star equals inverse t, 1 minus your percent confidence divided by 2, comma, degrees of freedom, just in case you need that. Okay, this is very rare in these problems. Most of the time you're going to have a sample standard deviation. So this is what you'll use. One of the small pieces of, I guess, what advantages that you guys will have because your test is going to be open notes is that you can use your own formula packet. So I just want to go over this real quick, where these things are located. So confidence intervals here. Statistic is the sample of what we're trying to find, a sample mean, plus or minus. Critical value is either Z star or T star, depending on if you have sigma or you have the sample standard deviation S sub x. And standard error of statistic can be located right here. So if you guys want to mark that, I will never know. Okay. Conclude. I did not want that comma, hold on. Wait for it. Wait for it. You know you've been excited to see it. Where is it? Oh, I know I brought it home. Okay, well, I'm not going to take more time. I do have a whiteout. I swear to you I do. Oh my goodness, I'm just getting even worse. Okay, mean. Context. We are blank % confident that the interval from blank to blank captures the true mean minutes and besides videos. Number of times that she screws up and needs to use the whiteout during a review. Okay, you guys. We are almost done. I'm sorry for the length of this guy, but has to be done. Okay. Okay, hypothesis test time. Okay, your null hypothesis is always going to be mu equals something. The alternative hypothesis is less than, greater than, or not equal to, depending on the problem. These two numbers will be equal, of course. This will be two-tailed, which means p-value times 2 at the end. Okay, you need to state your alpha level, and you need to state what the mean is that you are trying to estimate. Okay. Conditions are exactly the same as the confidence interval. I don't really want to go over them again. Random, independent, CLT related. Okay. The calculate. This is sort of the same, so if the population standard deviation is known, which is really, really rare, you will use Z. I don't know that I've ever seen this happen, but it's possible. Statistic minus parameter over standard deviation. Again, (99.9% of the time you are going to have the sample standard deviation, and you will use T. The top is the same, still your sample mean minus the parameter. Remember, the parameter is just this number right here, just plug it in. Sample standard deviation divided by the square root of n. Okay,